Let's jump right into this explainer because today we are pushing up against the absolute boundaries of science. We hold these sleek smartphones and ultra-powerful laptops in our hands every single day, but we rarely stop to think about the microscopic magic happening right beneath the glass. Today we're decoding the atomic limit. We're looking at the development of 0.7 nanometer chips. These are semiconductor processors built with components so incredibly small they are quite literally constructed at the atomic limit. To really wrap our heads around the scale we're talking about today, we have to start with the number 1 billion. Specifically, 1 billionth of a meter. That is exactly what one single nanometer is. And honestly, today we aren't even talking about a full nanometer. We're talking about 0.7 nanometers. At this level, the features on a computer chip are only a handful of atoms wide. It's a scale that just completely challenges human comprehension, yet it's the very foundation of our technological future. So why does 0.7 nanometers matter so much? Because this milestone literally saves Moore's law from dying. We've hit a physical wall with traditional silicon. You simply can't shrink standard silicon down forever. But by shrinking components down to just a few atoms across, manufacturers can cram billions of additional transistors onto a single silicon die. That is what keeps our exponential curve of technological progress alive and kicking. Here is how we're going to break this down. First, we'll enter the atomic scale, then look at printing the microscopic, battling quantum physics, exploring real-world tech impacts, and finally, examining the price of all this progress. Section 1. Entering the atomic scale, pushing the boundaries of computation. The goals engineers are chasing here are massive. The main objective? Increase transistor density. They want to pack billions more electronic switches into the exact same physical space to massively boost computing power. But, with great power comes the need for great efficiency. So reducing power consumption is key. Engineers are actively dropping the amount of electricity needed to move data across the chip. This naturally helps minimize heat generation, preventing your ultra-compact devices from just overheating in your pocket. All of this works together to enhance processing speed. Because the physical distance electrical signals have to travel is so much shorter, the chip can do its calculations significantly faster. And ultimately, this all sustains our overall technological growth. Let's move on to Section 2, printing the microscopic, manufacturing at the edge of physics. We are looking at a massive, massive shift in the industry right now. We're actually moving away from traditional silicon. It's just gotten too bulky and is reaching its absolute physical limits. Instead, the industry is pivoting to these wild two-dimensional materials like molybdenum disulfide or MOS2. Engineers are obsessing over these exotic compounds because they can conduct electricity perfectly at atomic thicknesses without breaking down. The craziest part? These 2D materials can form layers that are literally one single atom thick. It's an absolute game changer for signal transmission. But how do you actually get a single atom layer onto a chip? Well, factories have to buy incredibly advanced high-NA extreme ultraviolet or EUV lithography machines. These machines use high-energy light beams with hyper-short wavelengths and high-NA lenses to focus light precisely enough to print circuit patterns below 1 nanometer. Then, they use a chemical process called atomic layer deposition, or ALD. This process literally deposits materials onto the chip, one single layer of atoms at a time. The level of precision is just staggering. Section 3. Battling quantum physics, when rules break down. Seriously, think about this for a second. What actually happens to electricity when the channels guiding your data are thinner than a strand of DNA? When the ultra-thin structures called gates, which are supposed to turn the electrical current on or off, are barely even there? Well, the normal laws of physics that we're used to just completely change at this atomic scale. And that brings us face to face with the villain of our story, quantum tunneling. At 0.7 nanometers, the solid barriers meant to hold the electricity back are so unimaginably thin that electrons can literally accidentally jump right through them. Imagine trying to pipe water through a hose, but the water just decides to magically teleport outside the hose. That's essentially what electrons are doing here, and it causes massive data corruption, power waste, and totally unpredictable chip behavior. So to trap these rogue teleporting electrons, designers have to totally overhaul their schematics with major circuit redesigns. They're implementing ultra-thin gates and integrating new setups like backside power delivery to optimize the microscopic space. They're also stacking multiple chiplets vertically, but the most fascinating part? Teams have to design highly complex hardware and software error correction mechanisms directly into the chip itself just to detect and fix the data errors caused by this atomic instability. They are literally building real-time quantum cleanup crews into the hardware. Okay, let's zoom out a bit for Section 4. Real-world tech impacts, zooming out to your daily life. There's a very clear domino effect here. Step 1. Factories actually manage to manufacture these 0.7 nanometer transistors. Step 2. Designers can immediately place billions more of them onto standard-sized processors. Step 3. This gives us computations that are much faster and use way less lower power. Step 4. This scales up to create highly efficient data centers. And finally, Step 5. This massive power lands right in your hands, enabling advanced local AI and autonomous driving systems to run directly on smaller devices without needing to constantly talk to a remote cloud server. The practical results for you and me are pretty immediate. Think about extended battery life. Because the processor wastes far less energy, your smartwatches, laptops, and even medical sensors can operate way longer on a single charge. Then there's the smaller footprint. Hardware devs can build lighter, more compact gadgets with zero drop in performance. On a massive scale, we're talking reduced costs for huge server farms, drastically lowering their electricity bills and their carbon footprints. And maybe the coolest part, localized AI. Your phone can instantly analyze complex voice and video data right there on the device, which makes it faster and significantly more private. But of course, none of this is easy. Section 5, the price of progress, the risks of the atomic age. When you look at the major hurdles, the sheer cost is honestly staggering. Factories are dropping billions of dollars on specialized equipment and hyper-pure materials, which drives up the price of the final product. Then you have low initial yields. Manufacturing at the atomic scale is brutally tough, meaning a high percentage of early chips are just completely defective. We also talked about those amazing 2D materials, but they are incredibly fragile and very difficult to handle in mass production. Plus, packing billions of active transistors into a microscopic space creates intense thermal hotspots that can physically degrade the chip over time. And as always, that unpredictable quantum tunneling is constantly threatening to ruin the whole shebang. Which leaves us with this final, kind of thrilling thought to ponder. We've seen how 0.7 nanometer chips are saving Moore's law, battling quantum physics, and supercharging everything from your smartwatch to artificial intelligence. But as we manipulate the absolute final few atoms we can possibly work with, are we finally hitting the absolute limit of physics? Or is this just the dawn of a brand new atomic age in computing? Keep that in mind the next time you tap the screen of your smartphone. Thanks so much for joining me on this explainer today. Keep learning, keep questioning, and I'll catch you in the next one.